Section 20.7 Luminescence. A transition metal complex is luminescent if it emits radiation after it has been electronically excited by absorbing a radiation. One example is ruby. In ruby, mostly it's aluminum oxide, but some aluminum 3+ is replaced by a chromium 3+. So this chromium 3+ is surrounded by 6 oxidal ligands. And this structure may absorb green and violet lights and emit red light. That is why ruby is red. There are 2 different types of luminescence: fluorescence, phosphorescence. Fluorescence is a fast radiative decay. That means light emitting. So it's between 2 states of the same spin multiplicity, and this is spin allowed. And why it's fast? Phosphorescence is a slow radiative decay between 2 states of different electron spin multiplicities. And that's why this is spin forbidden and very slow. Now let's look at the terms of chromium 3+, surrounded by 6 oxidal ligands over here. The ground term is 4A2G. And then let's look at the first 2 excited terms with the same spin multiplicity. So it's 4T2G, 4T1G. And it's possible for this chromium 3+ to absorb a green photon to get to here, or a violet photon to get here. The energy gap is roughly 2.0 electron volts and 2.3 electron volts. 1 electron volt is roughly 96.5 kilojoule per mole. And now let's look at this internal conversion and intersystem crossing. So this internal conversion is non-radiative. So really this state loses thermal energy to surrounding molecules and get here. From here to here also it's non-radiative. Energy is lost in the form of heat. And this process is also spin forbidden process from a multiplicity of 4 to a multiplicity of 2. So this is a slow process. So how can spin flip be possible if the angular momentum of the electrons must be conserved? There are 2 possible reasons. One is spin-orbit coupling. So the electron spin flip can be induced by spin-orbit coupling. The spin angular momentum and the orbital angular momentum can be coupled. So that's reason 1. 2, this chromium 3+ complex may be surrounded by some other ions or atoms, and there can be exchange of electrons with opposite spins. So this is possible. And over here, this is 2EG. This is A42G. Again, these 2 have different spin multiplicities. So this red emission is called phosphorescence. It's a slow radiative decay because it's spin forbidden. In summary, ruby absorbs violet light, green light. That makes it red already. On top of that, ruby emits red light. So that makes ruby even more red and shining. So over here, this is essentially the same energy diagram. Ruby absorbs green light, violet light, and then undergo thermal relaxation. So from here to here, energy is lost in the form of heat. From here to here, Energy is lost in the form of heat. Also, you can go from here to here as well. This is the so-called metastable levels. Actually, this is just 2Eg term over here. And it can emit a red light at 694 nanometers. So this is why we can use ruby to make ruby laser to emit a red laser light at this 694 nanometers. This is the wheel of colors. So when a material absorbs green light in violet light, so absorb this light in violet light, so this material will look like a color between this and this. And on top of that, this chromium 3 plus emits red light. So this is ruby. That's why ruby is red. Again, let's look at the scientific reasons why ruby is red. It absorbs light at 258 nanometers. That will change the electronic state of ruby from 4A2G to 4T2G. So this is a spin-allowed electronic transition. It can also absorb violet photons and change its electronic state from 4A2G, the same ground term, to 4T1G. All right, so there's actually a symmetry change here from 2 to 1. Okay, at 408 nanometers. And this is violet light. And then you will emit red photons very slowly because this is a spin-forbidden phosphorescence process. It's from 2Eg. Over here, this is 2Eg to the ground term, 4A2G. That involves spin flip. That's why it's slow. And over here, this is the electron configuration. They look the same. But over here, you have alpha, alpha, alpha. And over here, you have alpha, alpha, beta, or alpha, beta, alpha, or beta, alpha, alpha in the dxy, dyz, dzx orbitals. And this transition emits a red photon at 694 nanometers.